If you know me in real life, then you can be like, oh, f you, Anthony. We hate you, you f for learning that stupid bullshit, that general relativity, gravity. Who the f do you think you are, you pretentious f you? There are no applications of knowing the math, being able to understand general relativity at a mathematical level. F you, Anthony. Okay. All right. What's up, you guys? Here we are again. It's been a while. I forgot what episode it is, but this is basically the last episode that I'm going to be doing in the couch style here. I'm going to go back to the traditional, if you will, like wearing suits and ties sort of stuff with the books in the background, or a green screen in the background, maybe not. I'm going to go back to that for the finale, which is the last 7 sections from Differential Geometry by Erwin Kreisig. So, kind of like I was saying in this ramble, this is the last couch episode because it's sections 88, sections 89, which are not on surfaces of constant Gaussian curvature. Yeah, anyways, I'm just going to get right into this. The last thing I will say, though, is that, okay, there's like 3 problems at the end of section 88, and then there's pretty much only 3 problems for the rest of the book in that last, like, surfaces of constant Gaussian curvature finale of the book, if you will. So, but after that, section 89, parallel surfaces, I'm really going to try to keep this short, but there's like 2 real world applications of differential geometry that I keep coming back to. One is obviously general relativity, and if you've watched my previous videos, then I've been thoroughly disgraced, debunked. You can completely discredit, write me off as a crackpot, because part of why I wanted to learn differential geometry was to learn general relativity. And so if you know me in real life, then you can be like, oh, f you, Anthony. We hate you, you f for learning that stupid bullshit, that general relativity, gravity. Who the f do you think you are, you pretentious f you? There are no applications of knowing the math, being able to understand general relativity at a mathematical level. You, Anthony. Okay, so the other application of differential geometry, it's like, okay, loud and clear, I heard it from everybody who I know in real life, who I've known maybe in like vaguely professional or engineering or academic, whatever. Anyways, the other application would be computational geometry. So that's like computer-aided design, computer-aided manufacturing. And that's what this book right here is. And long story short, this is from the MIT OpenCourseWare class for computational geometry, which weirdly enough is listed as like a graduate level mechanical engineering class. But then the entire grade that a student would get in this class, there's no exams, there's just 5 assignments. And the first assignment is basically like teach yourself differential geometry. And it's like due on like day 4 or day 5 of class, basically. And where this is all going is section 89 that I'm going to read from Erwin Kreisig. The biggest application that I could come up with is offset curves and surfaces. Specifically, when you look at these like parallel surfaces, which are basically just kind of like Bertrand curves, you kind of get like the involute, evolute stuff going on, but it's now you're doing it all instead of in the theory of curves, context of curves, as of the beginning of this book, you do it all with surfaces. But the application would be stuff like toolpath generation, feature recognition through construction of skeletons or medial axes of geometric models, definition of tolerance regions, axis space representations in robotics, rapid prototyping where materials are solidified in successive 2-dimensional layers, and brush stroke representation. So there will be definitely more about the CAD, CAM, computational geometry stuff for me coming up soon, but for now let's just get into this here. So section 88, center surfaces of a surface. We have seen in section 58 that we can associate three ruled surfaces to every given space curve. One of them, the tangent surface, is always developable, while the other two, the principal normal surface and the binormal surface, are developable if and only if the curve is plane. Similarly to every curve, capital C, with a vector parametric representation, x in terms of arc length, lowercase s, on a surface, capital S, which has a vector parametric representation, x in terms of u1 and u2, we can associate the ruled surface y in terms of s and this scalar parameter t, which is equal to vector x in terms of s, then plus parameter t, then times vector n in terms of s, generated by the normals to surface capital S along curve capital C. In the previously read expression for y in terms of s and t, lowercase s is the arc length of the curve capital C, and the vector n in terms of s is the unit normal vector to s at the points of C. If C is an arbitrary curve on S, then the expression for the ruled surface will not be a developable surface. In general, we may illustrate this fact by the simple example of a circular helix, capital C now, which gives a vector parametric representation which is entry-wise, 3 entries. We have r cosine of t, and then r sine of t, and then ct. On the cylinder of revolution, capital S, with a vector parametric representation x in terms of u1 and u2, which is now r times cosine u1, then the next entry is r times sine of u1, and then the next entry is u2. Since at every point of C, the unit normal vector n to s lies in the corresponding principal normal to the helix, the ruled surface, in the form which was read earlier, is identical with the principal normal surface of C, which is not a developable surface, for which we can refer to theorem 58.2, which, just for a recap, that is, the tangent surface is always a developable surface. The principal normal surface and the binormal surface are developable surfaces if and only if the corresponding curve is plane. We now come to theorem 88.1. The normals to a surface, capital S, with a vector parametric representation x in terms of u1 and u2, corresponding to a curve x of s of class r greater than or equal to 2 on the surface S, generate a developable surface if and only if C is a line of curvature on S. And the proof is as follows. The normals to S at the points of C generate a ruled surface, capital R, which can be represented in the form given above, the vector y in terms of S and t, by expression 58.2. Capital R is a developable surface if and only if the determinant, where we have entry-wise column vectors x dot, then n, and then n dot, and this determinant is then equal to 0. We assume the coordinates u1 and u2 to be chosen so that the coordinate curves are lines of curvature on S. Then x dot, which is equal to x sub alpha, then times u dot alpha, where that alpha is a superscript index, and then we have n dot, which is equal to n sub alpha, then times u dot superscript alpha, which this is equal to negative kappa sub alpha, then times x sub alpha, then times u dot superscript alpha. This is from the formulae of Weingarten. So inserting these expressions into the determinant that we have above here and simplifying the determinant, we obtain that likewise determinant where we have x dot, then n dot, is equal to now a determinant where similarly we have column-wise these vectors. So first we have vector x sub alpha, then times u dot superscript alpha. Then the next entry is kappa sub beta, then times vector x sub beta, then times u dot superscript beta. And then finally there's the vector n. And this then is equal to the determinant where, again, entry-wise, we have vector x sub alpha, then times u dot superscript alpha, and then next we have the quantity kappa sub 2 minus kappa sub 1 closed quantity, then times u dot superscript 2, and then finally the vector n. Hence, that determinant where we have x dot, then n dot in the determinant is thus equal to u dot superscript 1, then times u dot superscript 2, then times the quantity kappa sub 2 minus kappa sub 1, closed quantity, then times the determinant x sub 1, and then x sub 2, and then that is all equal to 0. Since x1, x2, and n are linearly independent vectors, the determinant on the right-hand side of what I just read does not vanish. Hence, in order that that above expression for what that determinant of x dot n and n dot equal to 0 all reduces down to, in order that that be satisfied of equaling 0, we must have that u dot superscript 1 is equal to 0. That is, u superscript 1 is constant, or u dot superscript 2 is equal to 0. That is, u superscript 2 is equal to a constant, or kappa sub 2 minus kappa sub 1 is equal to 0. In consequence of the choice of coordinates u1 and u2, the first conditions mean that C is a line of curvature on S. The third condition is satisfied if and only if the corresponding point is a navel point. And for those definitions, you can refer back to sections 41 and 48, which I did read in previous videos if you're new here. At these points, the normal curvature is the same for all directions. In an analogous manner, the converse can be proved. The lines of curvature form an orthogonal net, except at navel points, and to glean this we can refer back to theorem 41.2, which states that the lines of curvature on any real surface capital S of class r greater than or equal to 3 are real curves. If S has no umbilicus, the lines of curvature form an orthogonal net everywhere on S. Hence, in general, every normal to S is a generator of two of the developable surfaces characterized in theorem 88.1, which intersect orthogonally. The net of the lines of curvature consists of two families of curves. We consider one of those families. To every curve of this family, there corresponds one of the above developable surfaces. If each of these surfaces has an edge of regression, and if these edges of regression generate a surface, this surface is called a center surface of the given surface, capital S. Analogously, another center surface of S corresponds to the other family of lines of curvature of S. Hence, there are two center surfaces of S. And for this, we can refer to figure 94. Anyways, so yeah, that's a visualization of some center surfaces. There's two of them. We're moving on. In order to justify the name center surface, we prove the following. Theorem 88.2. The center surfaces of a surface are the loci of the center of the circles of principal curvature. Moving on. The proof of theorem 88.2 is as follows. The normals of a surface capital S corresponding to a line of curvature on S generate a developable surface. Refer back to theorem 88.1, which may be represented in the form of the ruled surface from the very beginning of this section. Expression 88.1, that's the vector y in terms of S and t. We have to determine the edge of regression, capital G, of this developable surface. That is, we have to find a function t, which equals t of s, lowercase s, of class r greater than or equal to 1, which corresponds to capital G, the edge of regression. If such a function has been determined, we can represent the edge of regression, capital G, in the form a vector y in terms of arc length, lowercase s, which is equal to vector x in terms of lowercase s, then plus the function t in terms of s, then times the vector n in terms of lowercase s. And differentiating this with respect to s, we obtain the vector, which is y dot equal to vector x dot plus t dot, which is just the scalar derivative of that function t in terms of s, then times the vector n plus t, then times vector n dot, which is tangent to the edge of regression, capital G. If n dot is equal to 0, that is, n is a constant, then the ruled surface representation 88.1 is a plane or a cylinder and has no edge of regression. We may exclude this case from our further consideration. We assume that the coordinates on capital S have been chosen so that the coordinate curves are lines of curvature on capital S, and that, in particular, the lines of curvature under consideration are the curves where U2 is constant. Then, by, again, the formulae of Weingarten from earlier in the book, vector n dot is equal to the vector n sub 1 then times u dot superscript 1, which is equal to negative 1 over capital R sub 1, then times vector x sub 1, then times u dot superscript 1, where this capital R sub 1 is equal to 1 over kappa sub 1. As kind of a recap, if I'm not mistaken, the formulae of Weingarten, it's kind of like another way of calculating principal curvatures instead of maybe going through the, maybe you want to call it like the direct Gaussian method of the first and second fundamental forms. So the formulae of Weingarten is kind of like a less conventional of the classic methods of calculating principal curvature. But take my opinion on that with a grain of salt. Moving on, since vector x dot is equal to vector x sub 1 then times u dot superscript 1 on the lines where u2 is equal to a constant, then this y dot vector we had obtained earlier takes the form vector y dot equal to quantity 1 minus numerator t over denominator capital R sub 1 closed quantity then times vector x sub 1 then times u dot superscript 1 plus t dot then times vector n. The generators of the developable surface have the same direction as the unit normal vectors n in terms of lowercase s and are tangent to the edge of regression capital G. Consequently, the vectors y dot and n are linearly dependent. Hence, in the above relation for y dot, the 1 minus quantity t over capital R sub 1 equals 0 must be true. That is, t is equal to capital R sub 1. Thus, this representation for our edge of regression now takes the form vector y equals vector x plus capital R sub 1 then times vector n. Analogous reasoning in the case of the other family of lines of curvature leads to lowercase t equals capital R sub 2. This completes the proof of theorem 88.2. We will now investigate some further properties of the lines of curvature and center surfaces and start with a preliminary consideration. Let capital C with a vector parametric representation x in terms of lowercase s be a curve on a surface capital S with a vector parametric representation x in terms of u1 and u2. Let lowercase t equal to x dot be the unit tangent vector, p the unit principal normal vector, tau the torsion, and tau sub g the geodesic torsion of capital C. And for that, we can refer back to section 50. If you're new here, I read the entire geodesic chapter in one go, so you can see that on my channel. It's a fun one. At the same time, I'm honestly a little bit weak on the concepts related to geodesics, like the Gauss-Bonnet theorem and stuff that was in there. Like, anyways, moving on. We consider any fixed point capital P of capital C. Let gamma, lowercase gamma, denote the directed angle from the vector P at the point capital P to the unit normal vector n of capital S at the point capital P, angles being measured from the unit principal normal vector lowercase p towards the unit binormal vector lowercase b to the curve capital C at the point capital P by expression 50.5 from the geodesic chapter, which is tau torsion times vector n equals the cross product between vectors n dot and x dot. So by that, we have here that tau sub lowercase g then times vector n is equal to vector n dot cross vector x dot. The unit binormal vector to capital C is thus vector lowercase b equals vector x dot cross vector lowercase p. And for that, we can refer back to section 13, but that's just like the definition of these so-called TPB frames. Like, what is even the definition of the relationship between the tangent unit principal normal and the binormal vector, right? That's just all it's referring back to. So we also have, going back to the early theory of curves chapter sections, you could have cosine of gamma is equal to the scalar product of p with n. So you have p dot n, not to be confused when I read that out loud with when there's the dot derivatives denoting here in this book. In the Kreisig book, a dot derivative is a derivative with respect to arc length lowercase s. And then conversely, a prime derivative would be with respect to a parameter like t, like just, real line parameterization. But in the CAD CAM MIT OpenCourseWare book, the convention for dot and prime derivatives is backwards. So that's a bummer. But anyways, and then it's confusing when I read those dot derivatives and then like a dot product, like a scalar product, as I just have here. Sine of lowercase gamma is equal to vector b dot vector n. Anywho, by differentiating this last relation and using relations from earlier sections in the theory of curves chapter and expression 88.9, which is that torsion times the normal vector equals the cross product of these, n dot and x dot vectors here. We finally have gamma dot then times cosine of gamma is equal to vector b dot scalar product with vector n then plus vector b scalar product with vector n dot, which is then equal to negative tau then times the scalar product of vector p with a vector n then plus the quantity where we have the vector x dot cross product with the vector p closed quantity, take the results of the cross product in that quantity and then do a scalar product with the vector n dot. This is all then equal to the quantity negative tau plus tau sub g closed quantity then times cosine of gamma. If the direction of capital C at this point capital P is not an asymptotic direction, then the cosine of gamma is non-zero, and we obtain the following formula of Binet, which is tau sub g equals tau plus gamma dot. So kind of like how I just skirted around in the geodesic chapter, this is arguably one of the most famous theorems in differential geometry, the theorem of Gauss-Binet. This is just off the dome, but it's like if you do the integral on some curve S, you're like on a compact surface presumably, and then you add the double integral on some portion, that equals 2 pi times the Euler characteristic, which is something like vertices minus edges plus faces, something like that. I totally butchered that, but in spite of me butchering it, it doesn't mean a whole lot to me right now at this moment, but it's a big differential geometry theorem. That's from the geodesics chapter. I mean, you could obviously say it's a result for proving if you have like a triangle on the surface of a sphere, the angles are going to be greater than 180 degrees. Similarly, if you have like a triangle on a so-called saddle surface or the surface of a Pringle or a hyperbolic surface, negative Gaussian curvature, then the sum of the interior angles of the triangle is going to be less than 180 degrees. To show that, you could use the Gauss-Binet theorem from the geodesics chapter. That's not what this is. But this is a theorem from the same, I believe the first name here is Ossian, O-Binet, O-S-S-I-A-N, I believe is the first name. At any rate, theorem 88.3 by Ossian Bonnet. Two parts. First part is, if two surfaces of class R greater than or equal to 2 intersect along a curve, capital C, which is the line of curvature on one of these surfaces, and if the angle of intersection is constant, then capital C, the curve, is a line of curvature also on the other surface. And part 2 of theorem 88.3 is, if two surfaces of class R greater than or equal to 2 intersect along a curve, capital C, which is a line of curvature on both surfaces, then the angle of intersection is constant. And the proof of theorem 88.3 is as follows. For the first part, let gamma and gamma star be the normal angles of C, capital C, the curve that is, for the two surfaces. We have that gamma minus gamma star is equal to a constant, and therefore gamma dot is equal to gamma dot star, where the dot denotes the derivative with respect to the arc length lowercase s of the curve. Let tau sub g and tau sub g, but then superscript star, be the geodesic torsions of capital C for the two surfaces. From the relations that we have above, we thus have that tau sub g is equal to tau sub g superscript star. From this and theorem 50.3, the first statement of theorem 88.3 follows. And so to recap, theorem 50.3 states that the geodesic torsion of a line of curvature vanishes identically. So for the proof of the second part of theorem 88.3, using the above notations, we have from the above relation 88.10, tau sub g equals tau plus lowercase gamma dot. We have gamma dot plus tau equals 0 and gamma dot star plus tau equals 0, or gamma dot minus gamma dot star equals 0. Hence, gamma minus gamma star is equal to a constant, thus the surfaces intersect at a constant angle. Easy enough. And we have theorem 88.4 by Joachim's law. The angle of intersection of a surface capital S of class r greater than or equal to 3 and a plane or sphere is constant if and only if the curve of intersection is a line of curvature on the surface capital S. In general, the principal curvatures 1 over capital R sub 1 and 1 over capital R sub 2 of the surface are independent of each other. A surface whose principal curvatures satisfy a relation of the form function capital F in terms of capital R sub 1 and capital R sub 2, that function being equal to 0 then, is called a surface of Weingarten. And for more, we can refer to the reference by Weingarten himself in the bibliography. Minimal surfaces are surfaces of Weingarten, and for the refresher, minimal surfaces are surfaces or portions of surfaces where there's a constant mean curvature of 0. Minimal surfaces are surfaces of Weingarten. For example, theorem 88.5. The center surfaces corresponding to capital R sub 1, for instance, of the surfaces of Weingarten of class R greater than or equal to 3 defined by one and the same relation, such as being in the form of a function in terms of R1 and R2, and that function is equal to 0, can be mapped isometrically onto one and the same surface of revolution. And now we have 3 problems here. Problem 88.1. Determine the coefficients of the first fundamental form of the center surfaces of a surface capital S in the case where the coordinate curves are lines of curvature on that surface. The solution of problem 88.1 is as follows. Classic plug and chug these coefficients here. The center surface of a surface, we're going to call it x for its vector parametric representation, corresponding to the principal curvature 1 over capital R sub 1 can be represented in the form vector y equals vector x plus capital R sub 1 then times vector n, for which refer back to from the main body of the section 88, expression 88.8. Looks exactly like what I just read. We choose coordinates u1 and u2 on x, the surface, so that the coordinate curves are lines of curvature. Then, in consequence of the formulae of Weingarten, the partial derivatives, where we have vector y sub alpha equals vector x sub alpha plus partial capital R sub 1 partial u superscript alpha, then times vector n plus capital R sub 1 then times vector n sub alpha, take the form vector y sub 1 equals partial r1 partial u1 then times vector n, y2 equals the quantity 1 minus numerator r1 over denominator r2, closed quantity, then times vector x sub 2 plus partial r1 partial u2 then times vector n. Hence the coefficients g sub alpha beta superscript star of the first fundamental form of the center surface under consideration are given by the expressions g sub 1 1 star equals the square of partial r1 partial u1, then g sub 1 2 star equals partial r1 partial u1 then times partial r1 partial u2, and finally g sub 2 2 star equals the quantity 1 minus r1 over r2 closed quantity squared then times g sub 2 2 plus the square of partial r1 partial u2. Similar expressions can be obtained for the coefficients of the first fundamental form of the center surface corresponding to 1 over capital R sub 2. So that one is very straightforward, I feel like. Calculating the coefficients of the first and second fundamental forms is just like all day in differential geometry, you know what I mean? Problem 88.2. Give another proof of theorem 88.3 using theorem 88.1 and then prove theorem 88.4. And I'm just going to do these both at the same time because then the follow-up to that is problem 88.3, prove theorem 88.5. So let's just get right into it. Let's just get right into these alternative proofs here, looking at the proofs in a different way from when we did in the main body of the section. So I'm just going to read these back to back here. Problem 88.2, but it's really proof of, what was it? Theorem 88.3, and then the next one's proof of theorem 88.4, right? Oh no, okay. Yeah, so this one is proving theorem 88.3 and theorem 88.4. The next problem, problem 88.3, we're proving theorem 88.5. So it's basically like we're just reproving everything in this chapter. So let's get to it. Let capital S sub 1 denote that surface on which capital C is a line of curvature. The normals to capital S sub 1 along capital C generate a developable surface, capital T sub 1. Refer back to theorem 88.1. Let capital G sub 1 be the edge of regression of T1. The surface T1 is the tangent surface of G1. Since C is orthogonal to the generators of T1, C is an involute of G1, that is, G1 is an evolute of C. What I tell you guys at the beginning about the whole Bertrand curves, involutes, evolutes stuff just coming back in surface form here. The corresponding tangents to two involutes of the same curve intersect at a constant angle. Refer back to theorem 22.1, which, if I'm not mistaken, is just literally stating, let vector y superscript 1 and vector y superscript 2 be two different evolutes of the same curve x of s. Then the angle of intersection of the tangents to y1 and y2 corresponding to any value of s is the same for all values of s. What I tell you. If we rotate the generators until they assume the normal direction to S2, we obtain a ruled surface T2. By assumption, the angle of rotation is the same for all those generators. Hence, G1 is transformed into another evolute of C, say G2, and T2 is the tangent surface of G2. That is, T2 is a developable surface. From this and theorem 88.1, it follows that C is also a line of curvature on the other of the two given surfaces. The second statement of theorem 88.3 can be proved in a similar manner. According to theorem 88.1, the normals to the given surfaces at the points of C generate two developable surfaces, T1 and T2, that is, tangent surfaces of two different evolutes, G1 and G2 of C. The corresponding tangents to G1 and G2, that is, the corresponding generators of T1, and intersect at a constant angle. Hence, the surfaces possess the same property. Since any curve on a sphere or in a plane is a line of curvature, theorem 88.4 is an immediate consequence of theorem 88.3. And here we go. Problem 88.3, which is another proof here, using theorem 57.1, which is an allowable mapping of a portion capital S of a surface onto a portion capital S star of a surface is isometric if and only if at corresponding points of S and S star, when referred to the same coordinate systems on S and S star, the coefficients of the first fundamental forms on S and S star are the same. So G sub alpha beta equals G star sub alpha beta for all of the values of alpha and beta. So using that, we have to prove that the first fundamental forms of the center surfaces, capital S of surfaces of Weingarten, capital W, let's say, satisfying the same relation, which is a function capital F in terms of R1 and R2 is equal to 0, can be transformed so that they become identical with the first fundamental form of a surface of revolution. Capital R represented by the vector x in terms of u1 and u2, which is then equal to, entry-wise, r of u1 then times cosine of u2, and then, next, r of u1 then times sine of u2, and then, next, finally, h of u1. We assume that capital S corresponds, for instance, to the principal curvature 1 over R1 of surface of Weingarten, capital W. Let x sub 1 equal R of U1 and let x sub 3 equal H of U1 be a representation of the meridian capital M of capital R in the x1, x3 plane, and let U superscript 1 be the arc length of capital M. Let R prime squared plus H prime squared equal 1, where the prime denotes the derivative with respect to u1, and ds squared equal du1 squared plus r squared times du2 squared. We choose coordinates on capital W so that the coordinate curves are lines of curvature. Then capital R sub 1 equals G sub 1 1 over B sub 1 1, and capital R sub 2 equals G sub 2 2 over B sub 2 2. For which refer back to expression 41.11, and partial B sub 1 1 partial U2 equals 1/2 times the quantity B sub 1 1 over G sub 1 1 plus B sub 2 2 over G sub 2 2 closed quantity, then times partial G sub 1 1 partial U2, and partial B sub 2 2 partial U1 equals 1/2 times the quantity B sub 1 1 over G sub 1 1 plus B sub 2 2 over G sub 2 2 closed quantity, then times partial G sub 2 2 over partial U1. And we can refer back to, so you have 46.3 prime, 41.6, 47.8 prime. So now by expression line 2 above, we have that partial B sub 2 2 partial U1 equals partial with respect to U1 of G sub 2 2 over a denominator of capital R sub 2. This is then equal to 1 over capital R sub 2, then times partial G sub 2 2 partial U1, then minus G sub 2 2 over a denominator of capital R sub 2 squared, but then this is then times partial capital R sub 2 partial U1. So by inserting the contents of line 2 into line 3, we thus have partial B sub 2 2 partial U1 is equal to 1/2 times the quantity 1 over R1 plus 1 over R2 closed quantity, then times partial G sub 2 2 partial U1. Suppose that R1 minus R2 is non-zero. Then from inserting the contents of line 4 that I just read into the contents of line 5 that I just read, we obtain G sub 2 2 over R2 then times partial R2 partial U1 is equal to partial G sub 2 2 partial U1 minus R2 times partial B sub 2 2 partial U1, which is equal to now a fraction. In the numerator we have R1 minus R2, and in the denominator we have 2 times R1, which is, then we have this fraction, take that, multiply it by partial G sub 2 2 partial U1. Therefore, partial with respect to U1 of the logarithm of the square root of G sub 2 2 is equal to 1 over denominator 2 times G sub 2 2, then times partial G sub 2 2 partial U1, which is now all equal to a fraction where we have a numerator R1 over a denominator of R2 times the quantity R1 minus R2 closed quantity. That's the denominator of this fraction, which now we have times partial R2 partial U1. And from this, now we take partial with respect to U1 of the logarithm of square root of G sub 2 2, then times the quantity 1 minus R1 over R2, closed quantity, and that completes what's in the logarithm, which after taking that aforementioned partial derivative with respect to U1, we now have still a partial derivative with respect to U1, but now we have the contents being the logarithm of the square root of G sub 2 2. That's the first logarithm in this partial derivative, but then plus a second logarithm, which is subject to this partial derivative, but the logarithm now is 1 minus R1 over R2. And once we resolve the partial derivative, we now have 1 over a denominator of R1 minus R2, then times partial R1 partial U1. So if we insert R2 as a function of R1 into this expression and integrate, we thus obtain G sub 2 2 then times the quantity 1 minus R1 over R2 closed quantity squared, which now equals E with an exponent of 2 times the integral of 1 over R1 minus R2, but then it's dR1. So using the answer to problem 88.1, we find the first fundamental form of the center surface is ds squared equals, so the first fundamental form is ds squared, or the induced metric is equal to the square of partial R1 partial U1, and then times the square of du1, plus 2 times partial R1 partial U1, then times partial R1 partial U2, that's du1 du2, plus now we have this larger outer quantity, inner quantity 1 minus R1 over R2, closed inner quantity squared, then times G sub 2 2, plus second inner quantity, which is partial R1 partial U2, close that quantity, square it, and then that closes the outer quantity, which is the third coefficient of the first fundamental form, because then that's times du2 squared. So another way of saying the first fundamental form of the center surface, we can have ds squared equals dr1 squared plus G sub 2 2, then times the quantity 1 minus R1 over R2 closed quantity squared, then times du2 squared, and dr1 is equivalent to partial R1 partial U1, then times du1 plus partial R1 partial U2, then times du2. In consequence of line 6 that I have just read, we thus obtain that ds squared is equal to the square of dr1, then plus e with an exponent of 2 times the integral of 1 over r1 minus r2, but that's dr1, and then we're done with the exponent, but we're multiplying it with the square of du2. Okay, so since capital W is a surface of Weingarten, then R2 is a function of R1 only. Hence, the coefficient of the square of du2 in what I just read above in line 7 depends only on R1 and is the same for all surfaces of Weingarten defined by the same relation, function capital F in terms of R1 and R2 equals 0. Consequently, the center surfaces under consideration are isometric, and the corresponding first fundamental form given by line 7 is of the type of that of a surface of revolution. This completes the proof. All right, and this is a relatively short section, so we're basically in the home stretch for the finale of surfaces of constant Gaussian curvature. Section 89, parallel surfaces. If segments of constant length are laid off along the normals to a surface capital S, all along the positive rays of the normals, or all along the negative ones, the locus of their endpoints in general is a surface capital S star, which is called a parallel surface of S. Obviously, if the vector x in terms of u1 and u2 is a representation of S, then vector x star in terms of u1 and u2, which is equal to the vector x in terms of u1 and u2 plus a times vector n in terms of u1 and u2, is a representation of S star. In the expression I just read, the vector n is the unit normal vector to S, and lowercase a is a constant. There exist infinitely many parallel surfaces of a given surface, each of which corresponds to a certain value of a. Parallel planes, concentric spheres, coaxial cylinders, and tori generated by a rotation of concentric circles about the same axis are simple examples of parallel surfaces. In all these cases, the surfaces have the same normals. We will prove that this holds for any parallel surfaces. Theorem 89.1. Two surfaces of class r greater than or equal to 2 are parallel surfaces if and only if they have common normals. The proof is as follows. We start from the representation which is above that I just read, assuming that a is a variable, and prove that if capital S and capital S star have the same normals, then a must be constant. That is, S star must be a parallel surface of S. We will see that a can be any constant, that is, all parallel surfaces of S are obtained in this manner. Since S and S star are assumed to have the same normal, then n scalar product with x sub alpha star equals 0 must be true. And so vector n scalar product with the quantity vector x sub alpha plus a sub alpha then times vector n plus a then times vector n sub alpha closed quantity is equal to 0, where a sub alpha is equivalent to partial a partial u alpha, where alpha is equal to 1 or 2. Since the vectors x sub alpha and n sub alpha are orthogonal to n, then from this expression that I just read, we obtain that a sub alpha is equal to 0. Hence, a is a constant whose value may be arbitrarily chosen. Every surface S star parallel to S therefore has the same normal as S. This property could have been taken as a definition of a surface parallel to a given one. To this extent, the concept of parallel surfaces is an analog of that of Bertrand curves. There you go. From theorem 88.1, we find that the lines of curvature on parallel surfaces correspond to each other. That is, these curves have the same parametric representation on all parallel surfaces if the coordinates u1 and u2 have been chosen according to the relation 89.1 that we started this section with. Moreover, it follows immediately from the investigation in the preceding section that parallel surfaces have the same center surfaces. We now come to another theorem from Ancien-Bonnet, which is theorem 89.2. Let capital S be a surface of constant Gaussian curvature, k equals 1 over r squared. Then there are two surfaces parallel to S which have the constant mean curvature h being equal to positive or negative 1 over 2r. The directed distances of these surfaces from S are negative, positive r, respectively. And the proof is as follows. The center surfaces of a surface are the loci of the centers of principal curvature. parallel surfaces have the same center surfaces. Consequently, if kappa 1 equal to 1 over r1 and kappa 2 equal to 1 over r2 are the principal curvatures of a surface capital S, then the principal curvatures of a surface capital S star parallel to S at the distance lowercase r are given by the expressions kappa sub alpha superscript star is equal to 1 over capital R sub alpha superscript star, which is equal to a fraction 1 over a denominator of capital R sub alpha minus lowercase r, where alpha can be equal to 1 or 2. By hypothesis, capital R sub 1 times capital R sub 2 is equal to 1 over capital K Gaussian curvature, which is equal to lowercase r squared. Consequently, S star has the mean curvature, capital H star, equal to 1/2 times the quantity kappa 1 star plus kappa 2 star closed quantity, which equals 1/2 times 1 over capital R sub 1 minus lowercase r plus 1 over capital R sub 2 minus lowercase r closed quantity, which equals negative 1 over 2 times lowercase r, which is equal to a constant. In an analogous manner, we find that the mean curvature of the surface parallel to S at the directed distance, negative r, is capital H equals 1 over 2 times lowercase r, which equals a constant. As an immediate consequence of this theorem, we obtain theorem 89.3. To a given surface of constant mean curvature, there exists a parallel surface of constant mean curvature and another one of positive constant Gaussian curvature. As follows from the expression 89.1 at the beginning of this section, the coefficients of the first and second fundamental forms of a surface parallel to a given surface can be represented in terms of the three fundamental forms of the latter, namely g sub alpha beta star is equal to g sub alpha beta minus 2a times b sub alpha beta plus a squared times c sub alpha beta, and b sub alpha beta star is equal to b sub alpha beta minus a times c sub alpha beta. For which refer back to 27.1, 38.4, 59.3. I'm going to pop those on the screen, and that's the end of section 89, and we are now at section 90, which is the finale, surfaces of constant Gaussian curvature. And yeah, I'll be all jazzed up and see you guys in the next one. Peace.